Cool. Good morning, guys. How's everybody doing? It's been a while, I feel like. Thanks for being flexible with everything. This past month has not gone according to plan at all. I guess that's just life. So appreciate you guys being on your toes with whether we're having class or not. Hopefully everything will be normal moving forward because we really don't have much to go. We're on lecture 17 today, looking at where we are in our calendar. What is this, week 13? So we're right here, April 14th. So really only 2 more weeks of lecture. So 4 more lectures after this one. And then we're going to be already over to finals and stuff. So again, just giving you guys a heads up so you don't hate me. This is not my decision, but this is just the way the class is structured. Our final will be at 7 a.m. Sorry, I don't like it either. But yeah, just start waking up earlier, like 15 minutes earlier each day, or 5 minutes or a minute or whatever you got to do to prepare yourself to use your brain at 7 in the morning. Start doing that now. Another few updates. Again, we're not doing this lab 8 anymore. Your lab 7, it was all virtual. Did everyone get a chance to see those? And everyone's working on that, and it makes sense, even though we're not seeing it in person. Lab 7, it should still be due on Friday at midnight. That's for everybody. So if you haven't gotten a head start on that, please do so. So no more lab 8. And then what I'm going to do is introduce lab 9, which is your individual lab. I'm going to introduce that here today, just so you can get a head start on that. That will be due, I think you'll have a few weeks to work on that. So you'll have, I think it's going to be due this Friday before finals week. It's nothing too extreme. It's not like a full project or anything, but it's, you're going to be working by yourself instead of your group. And it's kind of fun because you get to make it, your own project in a way. So we'll go over all that in a second. Did want to go over exam 2 recap. Overall, it's kind of cool. It was better than exam 1. So good job, guys. Actually, you guys did much better than last semester's exam 2. We did see an increase. You guys know I love good old box and whisker plot. On average, it was over 3 points increase. The whole class, if you sum up, how you did compared to exam 1, exam 2, everyone, there was a net positive 163. For those of you who maybe didn't do as stellar as you'd hope on exam 2, again, don't pay too much attention to the Canvas grade that automatically calculates, because that's missing the lab reports. Your lab reports, the cumulative of your lab reports counts as an exam, basically. So if you're the type of person who likes to calculate your grade and see how you're doing in the class, and see what you need to get or whatever that is, just don't forget about that lab report section, because that's not included in the Canvas auto calculate. Another big area to remind you guys of, the homeworks is 15%. So this homework coming up, please complete it, because we only have 4, maybe 5 homeworks. So if you're missing one completely, then that takes a big chunk out of it. If you haven't submitted a homework yet and you'd still like to, then please come and talk to me, and we can work on something as a partial credit at least. So yeah, just wanted to remind everybody of the course assessment percentage and everything, and to not rely on that Canvas, because the lab reports are going to be a little different. I did want to review just a few aspects of the quiz, or of the exam. If you guys have, or if you want to go in more detail with the problems, or understand my grading scheme or anything like that, I'd be happy to talk with you guys in office hours. So just send me an email or stop by my office hours, and I'd be happy to go through your tests in more detail. Just a few of these things. This one, you'll see, was kind of a trick question, and that's why I only took off 1 point if you got it wrong, because what this is looking for is classification, and a lot of you guys saw that you need to calculate the plasticity index, which is the liquid limit minus the plastic limit. You then have to check the A-line criteria, right? We know the liquid limit is greater than 50, so it's going to be a high plasticity, but it could either be a clay or a silt. And all of this stuff here, we see that it's actually above the A line. So upon just initial, investigation, just looking at this, you'd be like, okay, above an A line, it's a CH. But the thing to look for here that they like to put on the FE and on the PE is this one little detail that the percent passing is, or the percent minus 200 is 42 or whatever it is, but it'll be less than 50%. This is like a really easy thing that they like to put on the PE and FE because it's just this one detail. So since it's less than 50%, this means it's a majority sand still, right? Because remember, USCS, this dividing line is plus or minus 50% passing the 200 sieve. So for the USCS, it's just the majority. So if 51% is less than the 200 sieve, the majority is a fine, so we call it a fine soil. If the 51% is retained on the 200 sieve, then the majority is a sand, so we call it a sand still. So that's why this is not a CH, but instead this would be a CSC, a clay sand. So for clay sands or for silty sands, these are 12 to 50% passing. So anything within 12 to 50% passing here. I can hand them out after class, so don't worry about it. Anything from 12 to 50% passing is going to be a SC or an SM. In Florida, we come across SC or SM a lot because of this. Like 12 to 50% is a pretty big window, right? So a lot of times, like you could even get what seems like a clay, like in your hands, but it's actually an SC. So if it was below this line, then what we would have this would be an SM. So it's SC or SM. We don't care about plasticity, like in terms of liquid limit. So anytime you have a sand, basically the chart turns into something like this. So that A line is just to distinguish between either clay or a silt. So an SC or an SM. So just keep this in mind because this is a thing that they like to put on the FE or even on the PE because it tricks you got to think of that little extra step, and the PE and FE is just people trying to trick you the whole time for 4 hours. So just wanted to point that out. All right, the other one that I saw some issues on was this flow net. I know usually flow nets, the examples we've seen is flow moving horizontally, but flow nets can also be used in any direction, right? And this is a really common application for dewatering like a trench or something. So the big area that we have to remember, a lot of you guys saw that there was no issues counting the flow regions. So 4 flow paths and then all the drops. I think there's like 10 or something. I don't remember. But what we have to remember is this H is the difference in head. And if you ever need to worry about like, oh, I can't figure out what this is, just look at the difference between the triangles. So between the triangles here. So we have one elevation here. This is a triangle. And we have one down here that the water is keeping in. So our H, our total head difference, is both of these combined. So the HR plus the DT. So it's 35 meters. So just keep that in mind. These types of problems, again, are really popular on PE and FE because you have to think, they'll give you all these dimensions and you need to either add or subtract to determine the right difference in head for this. The other thing that I want you guys to always do is follow units. I always say that. And it's something that I didn't do in undergrad. I didn't really learn until grad school, but like literally 70% of engineering problems can be solved if you just put the units in and you know what you need to find and you know either to subtract or multiply or divide to get those units. So we know for this, we need to find cubic meters of something. If we put the units into this value, our K is, let's just say we put this into meters per second. So our K is in meters per second. Our H is in meters. And then our NF and our ND are just unitless. They're just numbers, right? So this means our K is what is called a flux. So it's meters squared per second. So if this is the equation that we know for flow net, and we need to get cubic meters, obviously we need to multiply this by another length. So that's where this 55 meters comes in. So the 55 meters again is length out of paper coming out of the screen. So if we multiply this by another meter, then we'll get meters cubed per second. And so this is a flow rate, how much volume of water is moving over a certain time. And we're given the time is 6 hours. So if the pump shut off for 6 hours, so this means we would just multiply this by 6 hours and then put it into seconds or whatever we need to. So our seconds would cancel out and what we would get is our volume. So you don't need an equation. You don't need to memorize anything here. All you need to do is follow the units and think about what you need to find and what you need to either multiply or divide by to get to that. I saw a lot of you guys doing like the kind of unit stoichiometry like this. If you're not familiar with this kind of like setup, then I definitely suggest doing this because it's easier in my opinion, like to cancel things out. You don't have to set it up like this, but especially like from taking like hours to days and stuff, like if we had seconds and then you do like 60 seconds is 1 minute, 60 minutes, 1 day or 1 hour, whatever that is. So just in my opinion, I think this is an easier way to keep track of your units. And then you just multiply everything on the top and then divide by everything on the bottom. And then boom, you have everything you need conversion wise, instead of trying to memorize like how many seconds are in a day or something like that. So I just wanted to throw these out and go over these because like, again, these questions are functioned or created from like what I remember from the PE and from the FE a while ago. So any questions on these? Again, I'd be happy to talk in more detail in office hours, but any like questions right off the bat? Everything else seemed pretty straightforward. These were just the two problems that I wanted to touch on. Okay, cool. All right, today we're going to be talking about capillary rise and how it changes the stress conditions. Luckily, I think a lot of you guys have covered capillary rise in was it fluid mechanics before, right? So that's from a like pipe standpoint or something, but in ground conditions, this is super, super important. So we've talked about already from the previous slides and previous lectures, how the groundwater changing can either increase or decrease our effective stress. And again, just to recap, the effective stress is the important stress for geotechnical engineers, because we are designing strength as a function of stress, and this stress is going to change with groundwater conditions. So we want to design our strength off of a stress that is taking out the groundwater, just assuming that it doesn't add or subtract any stress. So that's why we do effective stress instead of total stress in our design considerations. So this is assuming one thing though. This is assuming if we were to look right at this soil interface here, that it's a perfect line, right? Like we have 100% saturation versus 0 saturation. So completely air dry, and then it magically turns into 100% saturation. You can probably imagine that this is not the real, like the idealized case, right? Like we've already seen how moisture content is a thing in soil. Clays will have moisture content, sands will generally have moisture contents. So there's going to be some type of water that is in this pore space above our groundwater table that we need to account for, that can affect the stress. And what we know from 5th grade science, or whenever we took this, there is water surface tension as a property of water, the cohesion and the adhesion. Did anyone do that like thing where you take a penny and you put a bunch of water droplets on it? My wife was a science teacher and I remember always doing that and stuff. So we already know like that water molecules experience cohesion with each other and then adhesion with other molecules. So the cohesion is between similar particles, adhesion with other molecules. And we see this actually, due to this effect, we have what's called capillary rise. And we've all probably seen this with paper towels, right? Capillary, I don't know how to spell rise, where water seems to defy gravity, and since it's wanting to stick to each other, it moves up through this pore space. So we actually see the same thing occur in soils. If you think about it, a paper towel with all these small little pore spaces is very similar to soil with a lot of small interconnecting pore spaces. So this is actually the movement of water up into internal forces. And what actually causes this from a stress perspective is suction. So suction actually causes this. So if we're talking about a stress distribution, especially for pore water pressure, what this is actually causing is a negative stress, a negative pore water pressure that's moving the water up. And remember, if our total stress, or sorry, our effective stress is equal to our total stress minus our pore water pressure, this pore water pressure, this can change with suction. If this becomes negative, then what we're doing is subtracting a negative, and this actually increases our effective stress. So this is something that we need to account for in our total stress. So what they did long time ago, you guys have seen this before, where if you put a straw in water, the water will actually travel up the straw, and it's a function of the diameter. I don't need to go through all of this derivation of the function here. But in groundwater conditions and soil conditions, what we're assuming is this diameter of the capillary tube is very, very small. So the height at which the water will rise through a pore space is inversely proportional to the diameter. So the smaller the particle, or the smaller the pore space, then the more we'll see a capillary rise occur. So if we were actually draw the pore water pressure in this example here, what we would see is that below the groundwater table, so this is, again, the pore water pressure. Below this groundwater table, it increases like we'd expect, the height times the W. And above it, it's actually in 100% suction. So we just see this negative value. So we actually have a negative pore water pressure moving up it. So this isn't a case for looking at only pore space, so no soil. So in this case, we would actually see that this would increase the effective stress. So the pore channel is impossible to measure in soil, like if we actually think about it, right? Like we can get an idea of how the size of the pore channel, but we can't actually understand the exact length of a pore channel. It's just, there's too much variability in the soil conditions. What we do say is that there's some estimates of how much the water will rise in soil as a function of the effective size, or the grain size distribution. So it's a function of void ratio, and then this coefficient 10 to or 50 millimeters squared. And so these are just some of the accepted criteria. The big thing to remember is that the smaller the pore space, the more the capillary will rise. So the higher the water will rise above the groundwater table. So look at clays, for example. Hopefully by now we've seen like that clays are very, very small in pore size, and that creates a very, very small pore space between them. So we can have water sometimes rising 25 to 75 feet above where the groundwater table is. In coarse sand, like beach sand or something, we don't see nearly as much, 0.3, like less than a foot, right? Because the pore space in water the pore space in sand is much bigger compared to the water molecules itself. So this is why we usually assume that clay is 100% saturated if near the water table. Like in Florida, for example, the water table is never 75 feet below the ground surface. Maybe sometimes, but like most of the time, if you encounter clay, you're going to assume that it is 100% saturated because the water has like the capillary rise has occurred already in this clay layer. So unless already given to you, then you assume, or unless like, like tests were performed and it was provided, what you would do is you usually assume clay is 100% saturated if near water because of this. So over geologic time, capillary rise does not necessarily mean that the saturation is 100%, especially in granular soils. So if we have saturation of 100%, this means that we would just use our pore water pressure except in the negative term. So we would add a negative onto it, and the height at which it would rise, so our HC is going to be just multiplied by the density of water, and we subtract that out, and that would be our 100% saturation. So this would be our 100% suction too, right? Because it's just a pure negative pore water pressure. But sometimes we can still have a moisture content, and we can still have water being under capillary action, but we won't have pure 100% saturation. So we'll still have air voids in our mix. If that's the case, what we have is this equation. So what we just say is that the negative, or the suction, is the negative pore water pressure, or the suction, is just a percentage of whatever the saturation percentage is. So if it's the saturation percentage is 50%, then our pore water pressure is 50%. If it's 20%, then our pore water pressure is negative 25% or whatever. So it's a really easy, it's still a linear equation, even though realistically, we don't see this. So realistically, we see this curve if we were to plot the suction, but what we'd assume is a straight line instead. So we actually just assume that it's like this. That's okay unless you want to get into like environmental engineering, and then they have like soil saturation curves and all that fun stuff where they don't assume it's a straight line. They actually have the curve. But for our purposes in geotech, just understanding the stresses, it's usually acceptable to just assume this straight line and this function here. So again, this is assuming this is the straight line here, where UW is equal to negative in percent form. So then, this percent over percent, 100 times unit weight of water times the H. Again, unit weight of water something like that. So what we see here is, just to keep track of our equation here, usually this is our HC, so H for capillary, or lowercase hc. And then below it is our normal H of water, so like body of water. We're actually going, as we're diving down, we're going in only water, but as we go above HC, we're in the capillary zone, so there could be air. Let's just look at a really brief example here of this. I think I have two of them. Yeah, for this, we're just asked to draw the profile of total stress, effective stress, and pore water pressure. So again, our total stress is our sigma, our effective stress is our sigma prime, and our pore water pressure is U. So the total stress in capillary action will not change at all. So for our total stress, we can calculate it just like anything else. So at point A, we have 14 feet of a material that weighs 108 pounds per cubic feet. So feet times pounds per cubic feet, that means we have 1512 pounds per square foot. So that's our stress at point A. That's our total stress. Everything that it's carrying, our total stress. So the pore water pressure at point A, if we were swimming at point A, what we would feel is 10 feet of water above us, right? Because delta H, or sorry, the head is right here. So this would be our HW. We do not feel the capillary zone because this is unsaturated, or it's saying saturated here, but this is under suction. So it's not actually changing the stresses when you're 100% submerged, when you're under at like point A, for example. We'll see how that changes whenever we get closer to the groundwater table. But under the groundwater table, the U does not change. Again, just think of it like as if you were like swimming or something, like under 10 feet of water in a pool. If there was a little bit, and if somebody put a sponge on top of the pool and water starts soaking into the sponge, like there's not going to change anything like underneath the water. You know, you'll only have the stress changes at the surface. So for that, it's easy to calculate 624 pounds per square foot. So that means our effective stress is our total stress minus our pore water pressure, 888. So yeah. Okay. All right, so let's look at it at the surface. So let's just say this is 0.0. Sorry, I should have included that in the slide. So 0.0 or at our ground surface. Let's do the stresses in that location. So separate this. This is ground surface elevation, GSE. So our total stress at this location, how much are we holding up at 0.0? There's nothing above us. So our total stress is 0. You don't have to hold anything. You're doing good up there. Our pore water pressure, though, if this is 100% saturated, what we have is this negative HC. So we have 4 feet of suction occurring, and this is our HC. So we would have 62.4 pounds per cubic foot times 4, and that's negative. So we would actually have negative 25 pounds per square foot of pore water pressure. So if you want, you can just always use this equation here. Pore water pressure is equal to the saturation divided by 100 times the unit weight of water times HC. And this is negative here. You could always use this because if it's 100% saturated, 100 divided by 100 is equal to 1. So it's equal to the 100% saturation equation, right? So if you're afraid you're going to get mixed up, just always use this one and plug in whatever the saturation value is that is given to you. In this case, it's 100%. So that means our total stress at the surface is actually negative 25 pounds per square foot. Or sorry, our effective stress. So that could be problematic, right? If we have a negative effective stress, that means there's no actual intergranule connection. So a lot of times in a problem like this, they would actually put something on the surface to increase that stress, something that weighs 25 pounds per square foot, like it maybe just like one soil layer, a gravel layer, or something like that to balance out and shift all of the stresses back into the 0 or positive region. So if we were to plot these, since we're at 100% saturation, our total stress again looks normal. Our pore water pressure is going to have this, just like we were used to drawing last week, but now it's also going to have this negative section. So this negative section is again this negative S over 100 times the unit weight of water times HC. So that means our effective stress is also going to equal or have a negative section. But there's, so like one of the common problems that you'll see then is like, how do we actually determine what depth will we have a negative, or will we have negative? So like, what is this depth here of negative? And this is important because we need to either, like, we could remove this, we could add something to reinforce this area or something like that. So to actually do this, we need to do our like triangles from back in AP like triangle class in high school or whatever we took here. But we know that this value here is -25. We know that this value here is 888. So we know these two. We know the total depth is 14 feet. Pretend that's a straight line. It's 14 feet. So what we can actually do is set up a system of equations knowing that they share a similar apex, so similar angles here. Thanks to triangles, these angles are the same. So we just set up this system. Does everyone remember doing this back a long time ago? Cool. Did you ever think you'd use it in a junior level engineering class? Here we are. So what we do is just solve for x here, right? Solve for x. We'd see that x is 0.41 feet, and that's the depth then that we would care about right here. So this would be our x value. And that's important for us as engineers because we need to know how deep we may need to reinforce the soil with like soil nails or something against heave or blowout, right? Because if it's negative, we could potentially have movement of soil in this direction. So we need to keep that soil where it is. Yeah. What's up? Yeah, so when you're doing like triangles, you don't really need to worry about negatives or anything. So what we're doing is, this is technically negative, but it's the same as taking a triangle this way. Yeah, if you did this negative, then your x value would be negative, and that would be an issue. So with like triangles, we're just taking each one separately. So we're looking at this blue triangle, and we just care about the dimensions. So we don't actually care about the actual value, because it's strictly a geometry term. Does that kind of make sense? I feel like I don't know how to explain it. Let me get through this and maybe I can explain it a little bit more. But that's a good question because, yeah, you're right. The actual value that we care as engineers is negative. Like this pore water pressure is negative. But when we're using this tool of like triangles to analyze this geometry, arbitrary x, then we don't care about the negative, and it's just we're looking at the proportions of the shape. All right, so let's look at another example. All right, so we're given the capillary rise. These conditions here, we have a sand and then maybe like a silty sand or a saturated clay. Yeah, and then a sand. So there's capillary rise occurring in the sand. These dimensions are shown here. We need to plot the variation of total, effective, and pore water stress with depth. So we're told, we're just assuming that this is 100% dry. So saturation is 0. So there's no water in this area. Below that, though, we have a moist unit weight zone where the saturation is 50%. And then we have a saturated zone underneath that of 112 pounds per cubic foot. So what we do is if we need to plot the variation, so with depth of total, effective, and pore water pressure, we just take this one step at a time. So just take A, B, C, D. So let's start at point D. I always think it's easier to start at the bottom and think about like everything that is being held up, and then you just subtract them as you go. So at point D, we have, if we're doing our total stress, so sigma D, if you were hanging out at point D, what would you be feeling above your head? You'd be feeling 10 feet of this layer here. So that would be 112 pounds per cubic foot. You'd be feeling 5 feet, because this is 5. So let me just put these numbers here. 5 feet, 10 feet, 10 feet. You'd be feeling 5 feet of this layer. That's 120. pounds per cubic foot. And then you'd also be feeling 10 feet of the dry layer up above you. So 10 feet times 110 pounds per cubic foot. So if we check all of those units, feet times pound per cubic foot, everything would give us in stress pounds per square foot. This is equal to 2820 pounds per square foot. So the pore water pressure at D, if you were swimming down at point D, how much water would you feel above you? What feet of water would you feel above you? Who wants to say a number? 10 feet, yeah. So you only have 10 feet of water because we got the triangle there. So we have 10 feet times the unit weight of water, 62.4, since we're talking to Americans. And we have exactly from before, the 624 pounds per square foot. This means our effective stress at point B prime is 280.20 minus 624. And this is equal to 2196 pounds per square foot. So we take that, put it off to the side. We're good at point D now. Let me see how good I actually separated them. Wow, I didn't overlap anything for once. Sweet. All right, so point C. So we move up a little bit. We are now at the groundwater table. So for point C, our total stress, we've already calculated it, right? Because it's everything from this point moving on. What we can actually do is you can take the total stress and subtract out this section from point D, since we're just moving up and we're removing that. Or, if you'd rather, you can do the analysis from the beginning too. So let's just do that. So we have 5 feet of something that is 120 pounds per cubic foot. And then we have the dry section, which is 10 feet of something that is 110 pounds per cubic foot. So for our total stress, we have 1,700. So at point C, our pore water pressure. What would be the pore water pressure? How much standing water is above you at point C? What was it? None, right? Yeah. So you have 0. You have no standing water. I realize some of your guys' notes may already have this in there, but just bear with me as I go through it. So we have gamma W times 0, which is equal to 0. So we have no pore water pressure at point C. So our effective stress is just equal to 1,700 minus 0, which is equal to 1,700. So we move up to point B, and now at point B, we actually have to think a little bit further. So at point B, we have a transition zone. So if we were directly above point B, so just like move like a millimeter up above point B, you have no capillary, you have like nothing up there, right? If we go just below point B, then we would have some type of suction still. So the stresses below point B are going to be different than the stresses above point B. Now, realistically, this probably isn't the case, right? We're going to have a transition of suction from one point to the other. But anytime we're doing this type of analysis on paper, we're going to actually have to still draw that hard line at point B. So what we actually need to do is 2 types of analysis at point B. So we do point B above and point B below. So let's just do point B below first. So again, we're still saying this is at 5 feet, but picture it as like 5.999999999. So just barely below the point B line. So point B line. So our total stress at point B, I'm just going to put B for below. Still at point B, we say there's still 10 feet above us. And we have the 110 pounds per cubic feet. So our total stress at point B is 111. But our pore water pressure at point B below is going to be in this zone of suction, right? So that means we have negative, let me put the whole equation there. We use this equation, S divided by 100 times HC. So our HC in this case is still 5 feet, even though technically it's 5.9999999, round up for 5 feet. Our saturation is at 50%. So this is just equal to negative 0.5 times 62.4, and then times 5 feet. So this means our UB is equal to negative 156 pounds per square foot, which means our effective stress at B below is equal to 1256 pounds per square foot. Right, because we're actually adding on this now. We're subtracting a negative, so minus a negative 156. We actually have an increase in effective stress at this location. So again, what this is assuming, unfortunately, if we zoom in at this location here, what's going on? Let me erase all that. If we zoom in at this location at point B, what this is still assuming that there is a hard line. So we're still assuming, come on, go to red. It does. There it is, cool. Never remember what I delete or not. Anyways, at point B, they were still assuming that there's this hard line of capillary rise and not. So even though the whole capillary rise is to avoid that assumption of the groundwater table being 100% saturated and 0 above and below it, this hard dichotomy thing, at point B, we still have this issue. So at point B above, at point B, now let's look at it above. So what we're talking about now is like right here. Let's see what's going on here. Okay, so at point B above, let's just say this is sigma B A. Now our total stress is still the same. We have 110 pounds per cubic foot times 10. It's a 10, I swear. So we still have the same total stress. But now our B, our suction at this location is nothing. So we have no suction above this because there's no water. There's no capillary rise anymore. So this means our pore water pressure is back to 0. This means our profile is going to go from a value to 0, which means we're going to have a flat line. So we're still going to have this discontinuity of the profile. But that's okay. So this means our effective stress, whatever, it's going to be blue, is equal to 100 or 1,100 pounds per square foot. Okay, so at point A, everybody should already recognize by now, point A right here, our last one, the total stress is what's being held up above from point A? 0. Our pore water pressure is 0. And then that means our effective stress at point A is 0. So we got zeros all over. All right, so let's plot this let's like show the profile now. So to fill this in really quick, just to recap, at point A, we have zeros all around the board. At point B above, we have 1,100. We have 0, which means our effective stress is 1,100. At point B below, just below, we still have 1,100 here, but we have suction of negative 156 due to the capillary rise. So we're at 1256 for our effective stress. At point C, we have a total stress of 1,700. Our pore water pressure, though, is 0 because we're at the groundwater table. So this means we have this, and then below point C, it's just like normal from the previous lectures. Maybe I wrote that down wrong. I don't remember. We have all these values. So I think it's always easier first to put it in table form and then plotting it, just so you can double check your answers. So if we were to actually plot these now, what we would see is something like this. So again, the slope of our total stress, this slope here, is going to be dependent on our gamma of the soil, like whatever that is, dry, moist, saturated. If it is a higher number, we would expect to see that slope being wider, right? So a shallower slope because it's moving forward on the x-axis faster with depth. Our pore water pressure is the tricky part here because we have this zone of suction, which causes a negative value. Now, right at point B, remember, we have that discontinuity because of the directly above and directly below. So anytime we're actually showing this in plot form, we just keep it at the same depth. We just have 2 points. So if you're traveling, you're digging down. Right at point B, you hit a negative value at 10. So make sure to always include this value here. If you don't have this value, then it's going to plot something like this. And that's not correct because above that, we still have negative or 0 pore water pressure. So you need to include that second, value there so it shows that discontinuity. Once we get that, though, we have this changing in angle because this function again is S divided by 100 times unit weight of water times HC. So whatever our S is going to be dependent on this angle. If we have S equal to 100, then we have the widest angle. If that S is less, then we're going to have a different angle. And then our effective stress, again, we need to include this discontinuity here due to the effective stress. So you can see how this zone of positive capillary action will actually affect our effective stress. Any questions on capillary rise? Everyone's heard of like the concept capillary rise before, right? From other classes. Yeah.
What type of plays that were blowouts? Like say like low capillary rise. The battery and saturation.
Yeah. So blowout for clay is strictly just based off of a function of the density of the clay. Technically for capillary rise, it shouldn't really matter too much because capillary rise, what we're talking about is is like over geologic time. So like something that is like just part of the soil. Like this is just the soil has capillary rise. The blowout effect is more of a dynamic, like, shorter amount of time that can happen. So it could affect it because of the unit weight, but it wouldn't really play a role into it in terms of like the stress characteristics here. Yeah, besides that, like you can teach a whole class just on the mineralogy of clays, like kaolinite versus montemorillonite versus hillite. Like all of these different types of ite clays all have different molecular structures, all have different, granule structures, so they could have different capillary rise and stuff. But for us, we don't care about that. We're the geotechs from big scale looking in. So, all right. So what we've just been covering was vertical stresses. Again, we're zooming in here. Vertical stresses, if we have a load from soil above it, and we're assuming it's transferred through the intergranular stress, right? And this is our sigma prime. But then it ultimately transfers to something below it too. So if you took a scoop of sand and poured it on the table, what would you notice happen to it? Would it just only go vertically? It would also spread horizontally, right? So although vertical stress is super important, we also need to consider horizontal stress, because this type of loading is not just going to be transmitted perfectly vertically. We're also going to have these particles moving horizontally. So if we have this vertical, we would also have this horizontal section. Now, the question is, with water, we see this effect too, right? With water, we would also see the water pushing out this direction. But the interesting thing with water is that if you were to take water and pour it on the surface of a table, what would happen to that? It would spread completely laterally, right? So all of the vertical stress will be transmitted horizontally because there's no strength to it. It just falls out. Unlike with soil, if we were to pour it on a table surface, it would not spread out completely horizontally. There would still be some type of vertical strength holding it in place. All right, we are back thanks to lovely UNF Wi-Fi. Okay, don't know exactly where I ended. So what we were talking about was that there is vertical stress that is then transmitted through the intergranular stress and all that fun stuff. And what we actually have is a resulting horizontal stress too. So if we call this sigma V, what we'll just use is this horizontal H. This is also called lateral stress or something like that. And what we actually see is that this soil will produce a horizontal stress that is also increasing with depth. Again, I was talking about this. If you take like a cube of water, let's just say this is a cube of water, and it's not being bound by anything, and you put it on the table, what it would look like is it would just splat, right? It would like move horizontally. This is water. And all of this vertical stress will move horizontally. So what this is actually saying is that as this water is confined, this is water, the pore water pressure, or the W, or the U, sorry, is equal in all directions. Is all directions. And this kind of makes sense because, again, putting it on a table, it will splatten out. Splatten, if that's a real word or not. If we did this with a cube of soil, or let's just say this is sand, and we put it on, or we dropped it on a table, what we would see is it would look something like this, right? So we would see a little bit of movement horizontally, but there will still be some type of vertical stress.
we'll still see some type of vertical stress. So unlike fluids, the horizontal stress of soil, I'm just going to use the correct terminology. So sigma H horizontal stress is not equal to vertical stress. What we do see, though, is that it is proportional. So if we took our horizontal stress and divided it by our vertical stress, what we would get is what's called an earth pressure coefficient, this K. And this is just derived simply from knowing that our sigma H is equal to a constant times our sigma V. I remember, though, in geotech, we don't trust the water, so this total stress can change over time. So what we use is effective stress parameters. So our effective horizontal stress is equal or divided by our vertical effective stress is equal to this K value. And we put a little circle at the bottom. And this is our at rest earth pressure coefficient. So this not means it's at rest. Sometimes this is called K not as in like zero. I don't know where that term comes from. K naught. That's just what it's often referred to as. So this at rest earth pressure coefficient does not change in homogeneous soil. So it's constant with depth. So it doesn't change with depth. The typical ranges of these are anywhere from 0.2 to 0.5 in dense sands or clays. But if we have loose sands or clays, then this value is higher. It should be above 1. So 2 to 5. So think about what this is actually telling us here. If our K naught value is greater than 1, what does that mean for this ratio here? If it's greater than 1, that means our horizontal stress is actually going to be larger than the vertical stress. Now, if you look at these values, we see this occur in loose sands, and that should make physical sense to us, right? If we had a loose sand and we poured this loose sand out onto a table, onto some table, what we would see is this loose sand would spread out horizontally. So that's spreading out horizontally means the sigma H, the horizontal stress, is going to be more than our vertical stress. And we see that same with clays too. So this property, this K naught value, is really important property because this brings us from our vertical stress, which we can easily calculate, to our horizontal stress, which is important for structural loading. And I'll talk about some examples here. Structural loading, retaining walls, any type of foundation. This is a really important property. Now, this property is from, you can do triaxial tests. All these are crazy tests, but there's also some correlations that are really common to use. So if you have sands, then the most popular one is this K naught value. So our at-rest earth pressure coefficient is equal to 1 minus the sine of our friction angle. And we haven't talked about friction angle yet, this phi, but this phi is proportional to the strength of soil, specifically clay or sandy soil. So when you think of like strength of concrete being the compressive strength, or you think of steel, the strength of steel being the yielding strength of steel, soil is that parameter, or phi is that parameter for soil. So the higher the phi angle, the higher the strength, which means the lower the K naught value is. So the higher the vertical stress is compared to the horizontal stress. In clays and silts, we would use this as an example of a correlation. 0.42 times PI in percentage divided by 100. So our PI is our plasticity index, right? Which is our liquid limit minus our plastic limit. And this property is what we call an empirical, which means it is correlated using lab testing, and then a statistical function is fit to that correlation to use as a prediction. And remember, if you use this, where this PL is coming from. This PL, this is the Tootsie Roll lab, remember? The rolling test. So as sketchy as that test was, we still use it to correlate to a very important parameter called K naught. So just keep that in mind when you start working in geotech, or you work with a geotech. A lot of these things need to be taken with a grain of salt and with a little bit more of an understanding of where the actual value is coming from. Regardless, though, these correlations are good for clays and silts only. And there's lots more out there. If you take my design and analysis foundations class, that's going to be offered in fall of this year. It's kind of like the part 2 of this class. We talk a lot more on this K naught value. Let's talk about why we care about just stresses overall. So again, the at-rest earth pressure coefficient, our horizontal divided by our vertical, is equal to our K naught. So why do we care? Vertical stresses, it makes sense. Soil compressibility, so this is like the change in height at the ground surface or the settlement. Our soil strength is dependent on that, which is why we use our vertical. And then quick conditions. So when our vertical stress goes to 0, this could be issues with loss of strength. So this is something we want to go against. Horizontal stresses. This is when we start actually looking at the application of structures and everything. So like for this example, like a tunnel being built, we not only need to design this tunnel to combat against the vertical stresses above it, but also the horizontal stresses. So for like any type of tunnels or subterranean structures, horizontal stresses are very important for the actual design of these. The foundation strength is just as important too. Foundation strength, like for piles, for example, that friction on the pile is a function of the horizontal strength for tension piles or compression piles. So I'll just say for piles. That's another one would be for excavation. This is very, very important. Excavation. We don't really have excavations too much in Florida, but in the rest of the country where they have these things that are called basements, we need to change the ground surface elevation so we can construct into the ground. So we do this through retaining walls or sheet pile walls or something, some type of wall where we need to hold back the soil. And that soil we know now is going to exert a horizontal stress on this structurally. So if you think about this retaining wall, like we need to do a structural design just like we would for a structural analysis beam from our other classes. So this loading here is going to produce a force, right? This force is going to be called a P naught or a at-rest horizontal force. And this force is in like kips or pounds or something like that. And this is what we actually need to design against. If you think about this from a triangular load, like if this is just a triangular loaded beam, triangular distributed load, sorry, then we can create a function for this. Our P naught is equal to 1/2 times our K naught, our at-rest earth pressure coefficient, times this. This is this value right here, or at least sigma H, or gamma H is equal to this, right? And so it's base times height divided by 2 for the area of the triangle. And this is really important in the actual structural design. So this is super important for structural design to make sure that what we are designing or, structurally a retaining wall, something is not going to collapse. So K is crucial for design of retaining walls. K not. There's also other types of Ks called Ka active or KP passive, but we don't have time to really get into that. But that is talked a lot about in future classes and stuff, the strength of material or the design analysis foundations. So structural analysis to design bracing. Let's just show an example of where this issue could actually go wrong. Let's see. So this is an excavation. This is a massive excavation. I think it was in Turkey or someplace perhaps. Again, the whole purpose of this is to hold back soil so they can build something underground, like a basement, a parking structure, something like that. So this whole thing is designed based off of this K naught value, which is a soil property. You can see here, the soil is actually pushing so hard on the wall that it causes the bracing to buckle. And now you hear the popping of everything else starting to move. All right, who wants to guess what happens here? Well, of course, the issue with geotechnical structures is we design things that are massive and affect entire structures and communities nearby. So if this thing collapses in, then obviously it is affecting all the structures surrounding it too. So we have a lot of movement of mass of soil. And you can see it'll zoom in here. Oops. What do you think the property value of that? If it was in Jack's Beach, it would still be worth probably like $4 million. But here it's probably not good for the structure and the homeowners and everything else in the surrounding area. This guy's upset. He's like, oh, darn it. Oh yeah, so this is all based off of this K naught value or something similar called Ka probably. You can see why this is super important and why understanding the horizontal stresses are more important for design considerations and stuff. All right, let me see. I think that's all I have for this. What I do want to do now is if I can somehow. Let's see, everything is frozen. Okay, what I want to do, sorry, just a second. We have to switch this out a little bit. All right, what I want to do is, hopefully you guys are still there, go over our lab 9 really quickly and go over the details regarding this. Again, this is our individual assignment, so you're not working with your lab groups. What you're going to be doing is producing a site investigation report. The purpose of this is to investigate and present the relevant subsurface site information at a simulated project choice or project site of your choosing. So it can be anywhere you want in Florida. Preferably try to keep it in Florida. You can do other states if you want, but there's just not as much data available out there. It could be, your favorite restaurant, favorite place to go out to eat, favorite like landmark, driving around, your church, your house, your whatever you want, any location, you just choose it. And then you're going to be utilizing the subsurface investigation tools that we went over the week after spring break in those videos. So if you haven't watched those videos yet, you're going to have to because you need to know how to use these websites and tools for geotechnical engineering report purposes. So what you're going to do is choose a site first. What is the proposed purpose of the site? Could be what the current structure is, or just make something up. What do you anticipate the ground conditions to be like based on what you know about the project site? And why did you choose this location? So just for random project, for a construction site you drive by every day, whatever. The 4 things you're going to include is are you going to include the current satellite imaging of that location? So the map must be recent aerial images. You can use Google Maps, Bing, whatever you want, MySpace Maps, whatever. Historical aerials. So you're going to use the University of Florida's historic aerial database and look at the site that is pre-development, if you can. Some sites might be old enough that you aren't going to have pre-development. But the key here is to look for signs of potential problems later on down the road. Like, was there a pond that is now filled, cut canals or roads? Did it seem to be like a wetland or a woodland forest or farm, or a previous sinkhole that was filled in nearby? Like anything that is now buried to history that could affect the structure or the construction process moving forward. You're also going to be using the USDA link or soil survey, and you're going to map the area of interest. You're going to investigate only one of the soil physical properties. So in that video, I talked about all the different soil properties that we can determine from the USDA soil survey map. You're going to just pick one of those and explain why you wanted to use this one. Saturated permeability is usually the most popular one because you got to design stormwater and stuff in a project. And discuss the results of the physical soil property, why you chose this value, all this stuff. You're then also going to access the FDOT soil boring application and search your location and see if there's any nearby SPTs or CPTs or subsurface testing. If there is, then you're going to include a brief description of the subsurface conditions found and a description of your relevance of your project. So how far was the SPTs from your project site? Do you think the soil conditions are similar at your project site, so on and so forth? So I want you guys to be used to producing or using these online resources that are available for free, because these are the same ones that are used by professionals. So again, this is an individual report and it doesn't need to be super comprehensive. Just make sure you include all of these sections. You could do like a page for each one or a couple paragraphs for each one. And please still try to keep it professional with these format requirements here. So go ahead, you can get started on this one. It'll be due, whatever the week I said was due at the beginning of the lecture. I don't remember what I said. If there's any questions or you need help like picking a location, then just let me know and I can choose a random site for you to use if you don't want to try to find something on your own. All right, that's going to do it. Thanks for being flexible again with all me missing at the beginning of the week. And sorry if this doesn't record at all and the Wi-Fi is not working. So apologize in advance for that. I'll see you guys on Tuesday. Good luck, and let me know if there's any questions on this or on the lecture.